Today's paper is an empirical evaluation of in-memory multi-version concurrency control. It's a 2017 paper. This paper presents key transaction management design decisions in MVCC database management systems. There are four of them. The first is concurrency control protocol, second is version storage, third is garbage collection, and fourth is index management. For each of these topics, paper describes the state-of-the-art implementations for in-memory database management systems and discuss their trade-offs. It also highlighted the issue that prevents them from scaling to support larger thread counts and more complex workloads. As part of this investigation, authors implemented all the approaches in the Peloton in-memory MVCC database management system. Peloton was deployed on a machine with 40 cores and was evaluated using two OLTP benchmarks. The first benchmark is YCSP. Authors modified the YCSP benchmark to model different workload settings of OLTP applications. The database contains a single table with 10 million tuples, each with one 64-bit primary key and 10 64-bit integer attributes. Each operation is independent, that is, the input of an operation does not depend on the output of a previous operation. Authors use three workload mixtures to vary the number of reads and updates operations per transaction. The first is read-only, the second is read-intensive, and the third is update-intensive. The second workload is TPCC. This benchmark is the current standard for measuring the performance of OLTP systems. It models a warehouse-centric order processing application with 9 tables and 5 transaction types. Authors modified the original TPCC workload to include a new table scan query called stock scan that scans the stock table and counts the number of items in each warehouse. The amount of connections in the workload is controlled by the number of warehouses. There are 4 key contributions of this paper. Foremost is that the version storage scheme is one of the most important components to scaling an in-memory MVCC DBMS in a multi-core environment. It's observed that the performance of append-only and drive travel schemes are influenced by the efficiency of the underlying memory allocation schemes. Aggressively partitioning memory spaces per core resolves this problem. Delta storage scheme is able to sustain a comparatively high performance regardless of the memory allocation, especially when only a subset of the attributes stored in the table is modified. But this scheme suffers from low table scan performance and may not be a good fit for read-heavy analytical workloads. Second, using a workload-appropriate concurrency control protocol improves the performance, particularly on high contention workloads. Overall, multi-version timestamp ordering works really well on a variety of workloads. The third one is performance of a MVCC DBMS is tightly coupled with its GC implementation. In particular, a transaction-level GC provided the best performance with the smallest memory footprint. This is because it reclaims expired tuple versions with lower synchronization overhead than the other approaches. GC process can cause oscillations in the system's throughput and memory footprint. Finally, index management scheme can also affect DBMS performance for databases with many secondary indexes. Logical pointer scheme always achieve a higher throughput, especially when processing update-intensive workloads. Now let's give this paper a PS score. It's nice read with lot of experimental results and graphs, so readability it gets 8 out of 10. The overall paper is 12 pages long, so it gets 9 out of 10. The experimental findings in this paper, it'll be hard to reproduce, so it gets 6 out of 10. Industry value is high as there are a lot of practical results, so it gets 8 out of 10. I learned quite a bit about transaction processing design decisions, so on Learning Meter it gets 9 out of 10. So the overall PS score is 8 out of 10.